Hello students. So in this class we are going into more details about gravitational potential energy calculation. So gravitational potential energy, we have discussed about gravitational potential energy between two particles m1 m2 separated by distance of r. Gravitational potential energy is minus c m1 m2 by r. For system of particles where we have m1, m2, m3 mn, mn means number of particles is n, then potential energy will be calculated as 1 2 1 3, then 2 2 3 2 4. Here we are neglecting the cell potential energy. Like this you can calculate. So self potential energy is neglected here because they are particles. So if you neglect the cell potential energy, this is how many pairs will be coming? n minus 1 by 2. This is the number of pairs that will come. Okay, and we neglect the cell potential. Like that we can group and add. Okay, now what will happen if you consider Earth? Okay, what is gravitational potential energy? Gravitational potential energy of a body in Earth's gravitational field. So consider that this is Earth, let us say, and let us take particle which is you can take on the surface of Earth. Let us say on the surface of Earth. Then this particle is mass m, Earth mass capital M, let us say, and this distance is of course radius. So on the surface of Earth, the potential energy must be minus g m by r. This is at the surface. Of course, this small r is capital R. You have to put this as capital R. Okay. Now, what will happen if you consider particle at some height? Suppose this is Earth and the particle is here. It is at some height h, and this distance is radius. This is the center. Okay, Earth mass is at the center. So in this case, potential energy is minus c m by r plus h. This is at a height from the surface. Now you can take the change of potential energy. Like suppose for example you are taking from ground to top. Okay, so what will be the change of potential energy? Delta U. So minus g mn by r plus h minus g mn by r. Calculate this. What do we get? Let's calculate. So this will become plus, isn't it? So r into r plus h, and this gmm can be taken common. Then this is r plus h minus r, so it will become h times, right? So you may also write this as gmm by r 1 plus r by h, right? So I think this will become h by r because When you subtract this will become h by r. Check this calculation. Correct. Now I think here we can just keep this h and multiply this. Now it is correct, right? Yeah, so in this form you bring it, and now you can see that gm by r square is nothing but g, so it becomes mgh by 1 plus h by r. Correct. Now the change of potential energy when you lift a body from the ground to some height h is the formula, and if you consider if h is very small than r, then the change of potential energy just mgh, because you neglect in the denominator, right? So this is generally we are using the change of potential energy because on the ground we are taking as 0 level, right? So whatever the change is happening, that's the potential energy we are saying at the height h, because we take ground as 0, but actually potential energy is never 0. Potential energy is going to be negative. It is never 0, right? So potential energy is 0 only at infinity, right? Only at infinity potential energy is 0. So also if you consider potential energy at the center of earth, then what it will be? So at the center of earth, potential energy is equal to minus 3 by 2 gmm. Remember, this is like a solid sphere, uniform solid sphere. You can assume it like this. And if you take some depth h below, let us say here, if you want to take, suppose this is center and this is the distance center. How does potential at that point will depend? So it's just potential at that location is nothing but mass into potential energy, mass into potential at that place. Okay, so you can multiply potential at that place and you remember the formula for potential. So minus gmm by capital R 3 by 2 minus r square by 2r square, right? Is the formula, only m is getting multiplied here. So just like potential due to solid sphere changes, same way potential energy due to solid sphere changes, right? So minimum potential energy is at the center. You put a small r0 here, you will be getting this, right? Okay, this is about with respect to the earth. Then next let us understand what is self potential energy. Self potential energy. So suppose we will take one case, a solid sphere. We will take solid sphere. A solid sphere, let us say this is a solid sphere, and the radius of this solid sphere is capital R. Okay, and how this mass is built up? So initially, let us, there was no mass, and you are building mass or bringing mass from infinity. Small masses we are bringing it from infinity, and you are building up its radius. And let's say at a given instant, its radius is small r. Small r is the radius. At a given instant, the radius is small r. Okay, so you are bringing a mass, isn't it? You're bringing a mass and you're putting it on its surface, right? So what will be the work done? Already this is filled up to this small radius r. It's filled up, and now you are bringing a small mass dm and you are putting over its surface. Because you are putting it over the surface, its radius is changing by dr, right? So this mass which you are bringing it, what is the work done? That is the potential energy. So that is small change of potential energy that is happening here is nothing but the work done, right? And that work done is minus g. Already it has some mass, let's say smaller, so gm, and gm by r, right? gm by r. This is the potential of this, and you are bringing that small mass, so gm dm by r, correct? That's how we can see that. Okay, so minus gm by r is the potential, and the small mass which we are putting it over its surface, that is the mass into this potential energy. Now we need to integrate it. That will be the total potential energy or self potential energy. Now here this mass or radius we have to write in terms of that density, right? So what is this small mass? This small mass is equal to density into small volume. Small volume which we are building up can be written as 4 pi r square dr. Okay, so we can convert it in terms of that dm, and this mass which is already there, which can be written as density into volume, 4 by 3 pi r cube. Assume that you are keeping the density as same, constant density, uniform density. So minus g, and is rho into 4 by 3 pi r cube by r, and dm can be written as rho into 4 pi r square dr. So what do you get from here? Minus g, rho into rho square can be taken, right? 4 pi will become 16 pi square, by 3 is also a factor which is coming. So inside r power 3 to 5, and you have to subtract 1, so r power 4 dr is coming. Let's say radius we are building 0 to capital R. So this is what you will be getting, the self potential energy. Now you can integrate, isn't it? So how much do you get from minus g rho square into 16 pi square by 3? This will become r5 by 5, correct? So the final potential energy of a solid sphere is minus g, factors you can bring first, 16 by 15 pi square g rho square, right? R power 5, correct? That's the formula for self potential energy of a solid sphere. This is the formula for self potential energy, gravitational potential energy of a solid sphere. Okay, where rho is the density. Now this rho can also be put in terms of mass. Density is equal to mass by volume, 4 by 3 pi capital R cube. You can substitute that. So it will come as, how much it will come? You can just simplify that. will come minus 3 by 5 g m square by capital R. After simplifying this it will become. Okay. Same manner you can calculate for hollow sphere, right? For a thin hollow sphere can also be calculated, isn't it? So if you calculate for a thin hollow sphere, that also you can derive using the same approach. Okay. Let me write the formula for that. For a thin hollow spherical cell, self potential energy U will be minus g m square by 2r. Here m is the total mass of that hollow sphere. Okay. So this formula we can use. You can try to prove it in the same way. Right? So in this manner we will be able to do the calculations, right? So this is one topic that we can do. Then we can go for the escape velocity, calculations of escape velocities. Escape velocity. What is escape velocity? Is the minimum velocity by which a body projected from Earth's surface can escape Earth's gravity. So suppose if this is the surface of Earth, right, and from here you are projecting a body. This body has mass small m. Let's say we are projecting it with the velocity v. This is the escape velocity. So it should escape, that means it should go to the very far away. That means right now the distance x is r. It should go to infinity. X should become infinity. And minimum means it should stop there. After going to infinity it should not move. That means here final velocity should become 0. So you can apply the energy conservation. If you apply initially it has kinetic energy half m v escape square. It has also potential energy minus g m n by r. And finally the kinetic energy is 0. Finally the potential energy is also 0 because it's infinite distance. So let's balance the energy, total energy. So total energy initial is equal to total energy final. So initial energy is half m v escape square minus g m by r, and this is going to be 0. From here you can solve the escape velocity. Mass will get cancelled. So 2 gm by capital R. It can also be written in terms of g by writing 2 g into capital R, right? So this escape velocity in terms of acceleration due to gravity and in terms of total mass, in terms of densities also you can write. If you write mass as density into volume is 4 by 3 pi r cube. So escape velocity can be written as 2g rho into 4 by 3 pi r cube into r. So escape velocity will become root under 8 by 3 pi rho g, and this become r square, right? R square can be also taken outside. Correct? So 8 by 3 pi rho g R square. Okay, sometimes questions can give in terms of density, not in terms of mass. So according to that, you can use this escape velocity formulas, right? It is not only for Earth; it can be for any other planet. To escape an object from that planet, this is the escape velocity. Remember, the final energy is total energy is getting 0. That's why we are getting this equation, right? So thank you for your attention, and we will see the next time.